In this video, I would like to discuss the questions asked on complex numbers in JEE Advanced 2022. These questions are very beautiful. So I would like to show you different approaches in which you can do these questions. And of course, my favorite approach would be the geometrical approaches. So let's talk about the first question here. Z is a complex number with non-zero imaginary part. Okay, so it's not on the number line and not on the real number line actually. So if this is a real number, this expression is a real number, then what is the modulus of z squared? So that's very interesting, because if this is a real number, the output of this is a complex function, right? You put something inside it, a complex number, and usually you will get out a complex number, but they say that this expression is giving you back a real number. So what is the modulus of z square? In a way, a more general question would have been, what is the locus of that z? Well, the input z. But let's see how we can do it. The first approach is algebraic approach, which is like you can take z is equal to x plus iy, where x and y are real numbers, and from here you can build up this expression. So you can think what z square is, and then you can make these expressions. This will take a little bit of effort, but when you go into something, I say like go in it fully and come out with an answer. So now we have this expression here in terms of x and y, and then you see that there is a denominator here also, so you want to express it in terms of a plus ib, so no denominator, so then you can multiply the conjugate, right? So then this is where it gets very cumbersome, but still you can manage, because you don't have to think about the real part. There will be some real part, but the imaginary part should be 0 according to the question. The output, this expression should be a real number, so the imaginary part should be 0. But you also have to see like whether this denominator is going 0 or not. It should be non-zero, right? So we'll do a quick check on the denominator. So you see, for denominator to be 0, this is a sum of square of two numbers, right? Two real numbers. Sum this squared, this is square here, and this is a whole square of 8 into 8x minus 3 into y. So this will be 0 only if this is 0, this expression is 0, and this expression is also 0. So you solve the second one first. Y, it gives you that y is equal to 0, or x can be 3 by 8, but y is not equal to 0 as stated in the problem. So y is not 0 because the complex number, original complex number z is equal to x plus iy, has a non-zero imaginary part that was stated in the question. And then x is equal to 3 by 8, and then we take this x is equal to 3 by 8 and put it in this other expression. What do we get? So we get that 4y square. It simplifies down to this thing, 4y square, and this thing is negative, this number is negative, right? 9 by 16 minus 6. So this cannot happen in the realm of real numbers. So what does this guarantee? This guarantee that you have such a condition that this denominator will never go to 0. So we are safe now. So we can just take the imaginary part and put it equal to 0, and this will give us this equation. And from here you see it gets more cumbersome, but it's not that difficult. You can manage it still and cancel out things. You see the 4 terms are going to get cancelled out, and then what you will remain with is a very nice expression in x squares and y squares only, with some constant terms, and you rearrange them and you get that x square plus y square is equal to half, which is what they were asking, like what is the mod of z squared. So x square plus y square is mod of z square, right? Because mod of z is going to be root under x square plus y square. So because z was x plus iy, right? So we have got the answer, that is half. But then if you are not if newbie in algebra, so you would not like this kind of solution, because you must have done this kind of things many times. But then you see that sometimes when you look into geometry, and you get very elegant solutions. So the second solution is a pretty elegant one, and for this I am using like this idea that this expression is a real number. Geometrically I can say that if a complex number is a real number, then its argument is n pi, right, n pi, because if it's a positive real number, its argument it's somewhere here, so its argument is 0, or maybe you can say 2 pi plus minus 2 pi, you know, or plus minus 4 pi, something like that. So you have the even integers of pi, and if it's a negative real number, then you have the argument of negative real numbers would be minus pi, plus minus pi, you know, and plus minus 3 pi, things like that. So understanding that, we say that the real numbers have an argument n pi. Okay, so now you see this argument, I will break it down to this. It's one complex number 4z squared plus 2 minus 3z, and then the other complex number, same complex number 4z squared plus 2 minus 3z, right? So this breaks it down to this form, argument of z minus z1 by z minus z2, and this is a very special form. What is the meaning of this argument? So I have a separate video in which I discuss this form of argument. I think even more general form I have discussed in that video, and this is how I like to think about arguments. As so you can have all the 4 numbers different also, z1 minus z2 by z3 minus z4, and this argument means something special. So I would post the link of that video in description, you can go and watch that, but here I would explain this thing. So you have this numerator vector you can define here. So joining z from z1, okay, this is how you make this vector, and so you make this vector like this, and then the denominator vector is like joining z from z2 like this, and then what you measure is the angle between these two vectors, and you go from denominator to numerator, because the sign of the angle also matters here, if it is positive or negative. So I will go from the denominator vector z minus z2 to z minus z1, and this angle is represented by this argument. Okay, so now what we see that in our expression the z1 and z2 are not very independent. The z2 is negative of z1, right? And when this happens, so geometrically you should know, like when a complex number is completely the additive inverse of the other complex number, then they should lie on the same line which joins the origin, right? So I mean, if z2 is minus z1, then it should be the reflection of z1 about origin, like here. Okay, so we need to redraw this, and then we see that this is representing, this expression is representing this angle. Okay, but according to question, this angle is going to be n pi. So it could be, it should be 0 or pi or 2 pi, like that. But here you see that there is some positive angle, sorry, negative angle, because we are going in clockwise direction. It could also be expressed like a positive angle if you go from here to here. So that's a triviality with angles, that you can add and subtract 2n pi, and then they will still remain the same. So not going to go into that, it's simply this angle, okay, but this angle is going to be n pi. So if this angle is going to be 0, where should be this z? Where should this z be? 0 or pi or something like that. You feel that these two vectors which are connecting z1 and z and z2 and z should get parallel or anti-parallel. When will that happen? Right? This is not going to happen when z is here. Okay, this will happen when your z is on the line joining z1 and z2. So your z should be on this line. It should be in between z1 and z2. When it is in between z1 and z2, you will get anti-parallel vectors, and the angle between them will be odd multiples of pi. Like here you can see you can say that this is minus pi, sorry, plus pi if you go anti-clockwise, and if you go clockwise you can say this minus pi, and then you can do a complete circle and then come back, like you can say this is plus 3 pi also. So you can do things like that. So basically your z should be on this line joining z1 and z2. It could also be here. So then you see that the angle will be 0 or even multiples of pi. So this is the condition. So it boils down to that these three complex numbers should be collinear. This one and this one, right? Also, so I have not written minus 3z here because 3z and minus 3z are on the line joining origin. So I have taken the simpler complex number 0, right? Also, I will say, because we have this special line joining the origin, if suppose my 3z is somewhere here, it's this kind of a line from origin, and 3z is somewhere here. If I take only z, if I remove this 3, so my modulus will be decreased by a factor of 3. So it will also be on this line, right? Similarly, for 4z square plus 2, you can take out this common term. It's 2 times 2z square plus 1, and you can remove this 2 because we are on a line joining the origin. So we can do that. So this boils down to this very simple thing, that 0 and z and 2z square plus 1 must be collinear. So from here, let's go into coordinate geometry, and let's say that z is this point, then z square is this expression, and you can think in terms of coordinate geometry. So you can represent the z by this point x comma y on the plane, Argand plane, right? And you can represent this complex number by this being the x coordinate, 2x square minus y square plus 1, and y coordinate being the imaginary part, 4xy. So you can represent these 3 points, 0, 0, x, y, and this, and you will put a condition of collinearity. So you can write this slope first, this section, that would be y by x, and then the slope of this section using origin and this point, simple y2 minus y1 by x2 minus x1 kind of a thing, and then you can get your expression. As y is not equal to 0, you can cancel out these two y's, and then you will get this same answer, x square plus y square is equal to half. Well, so you saw in this solution we first used geometry and then we moved into coordinate geometry. But what if we use more geometry, pure geometry? Let's see. So we have z at an angle theta. We have a complex number and its argument is theta. When we square it, we get a number, a complex number, which has the argument double than the first number, right? So this z square will be on this line. It could be of the same magnitude. If mod z is equal to 1, then your modulus of z square would also be 1. So they would lie on this circle centered at the origin, but it might not be the case when mod of z is greater than 1 or less than 1, right? So, and then 2z square you can plot like here. It can move even, it will move of course farther, because the modulus will get twice than of the z square. So something like that. Then you think about 2z square plus 1. So when you add 1 on a complex number, you have to move distance 1, right, towards the positive x-axis. So there is your 2z square plus 1, and you see that these 3 points, the origin and z and 2z square plus 1, should be collinear. So that's why we come back to the line which connects origin and this complex number z. Okay, and now from here we have certain angles and we can do some geometry. We can join this, and then we can say that this is x. Suppose this length is x, and this length will be 2 times x square, right? These lengths you can calculate using modulus. So mod of z is x. If mod of z is x, so mod of 2z square, what would be that? So 2 you can take out, and this will be mod of z, and square you can just put outside. So you will have 2x square, right? So that length is 2x square. Great. And then do you see these two parallel lines here? And from here you can understand, you can join this, complete this triangle, and you can think that that angle is also theta. So what you get here, you see, what you get here, that OAB is an isosceles triangle. Triangle OAB is isosceles. And because of that, this angle, these two angles are equal. So because of that, these sides should be equal. So you get Very simply, AB is equal to OB, and then 2x squared will be 1, so x squared will be 1 by 2. What is x? X is basically mod of z, right? So mod of z squared is half. So when I do more and more geometry, when I put more and more geometry in my solutions, I get very elegant solutions, and no doubt, because geometry is one of the most ancient studies and very visual, and even people back then could relate with geometry. So of course modern people can relate with geometry also. Okay, so let's move on to the next question. This question is very interesting. It's there is a very good, very beautiful geometry going beneath it. We will discuss that. So what is the question? If z bar denotes the complex conjugate of a complex number, okay, and iota is this, fine. If the set of complex numbers, the number of distinct roots of this equation. So this is a complex equation, and you have to solve it, and you have to figure out what are its, how many roots does it have. And here you can also figure out the roots exactly. So I see many students, they like going on, they check some random values, and there is like in the realm of complex numbers, do you have this thing that if you have a polynomial of degree 2, then you will have only two solutions, exactly two solutions, which is called the fundamental theorem of algebra? Well, that's a nice question. You need to think about that. But anyways, we don't have only z, we have z bar also here, so it's a complicated kind of a question. Somebody might have thought that this the degree of this equation is 2, so we should go with answer 2. But I don't think that will hold here, because I have solved it. It's a beautiful, beautiful question. Let's start by rearranging the equation. So z bar, you take these terms which have z bar in them at one side, and you simplify it to this. 1 plus I by 1 minus I is going to be iota, right? You can just multiply the conjugate and check. So you have this equation. This is in simplified. This is the same equation simplified. Z bar is iota times z square. Now I am again going to use geometry, because if I know where my z is, I can know where my z bar is. So if my z is suppose here on the complex number plane, my z bar will be here, right? Reflection about the x axis. So, and z square will move. If this is angle theta, z square will have an argument of 2 theta, and it could be on this line like farther or closer depending upon what is the modulus. So z square, we can know z square is on this line, this we can say. So we know these things about, if we know these things about the geometry of complex numbers, then we can understand. And then one more thing is like when you multiply I, suppose your z is here, and where is iz? So when you multiply I is basically e to the power I pi by 2, and let's say your z is some r times e theta. So you see that this theta will get added in this argument. So my iz should be anti-clockwise pi by 2 ahead here, right? So these concepts, if you know these concepts, then you can solve this question in a much more interesting way than going into the algebra. So what they are saying is that the z bar, the conjugate of a complex number, is pi by 2 ahead in phase, pi by 2 ahead in argument, or phase you can also say. I like the word phase too. Pi by 2 ahead in phase than z square. Okay, this is the equation. Okay, first let's think about the what should be the modulus of this z we are talking about. So when you take modulus on both sides, the modulus of conjugate is same as the modulus of z, and iota, this modulus will distribute on the multiplication, and iota has a modulus 1, so you will get this thing. And then you have only two situations, that mod of z is either 0 or 1, right? And if mod of z is 0, then you can say z is 0, and z is equal to 0. It actually satisfies this equation. You can put it here, it will satisfy, of course. So this is a trivial solution. So you have got one solution, but the other solutions are on z is equal to 1, right? So all the complex number on the unit circle. So these complex numbers on this circle can now be the solution of this equation, but which ones? So we can take z. We can start from this complex number 1. This is z is equal to 1, right? We can start from 1 and then start going around the circle and see what happens. So we have z. If we have z is equal to 1, then we have z bar also is equal to 1 at the same point, and z square is also 1. Now if you move your z a little bit, so at an angle theta, your z bar will move same angle. If this moves here, this will move same angle in the opposite direction, right? Because of the geometry of z and z bar. And z square will move, and it will remain on the unit circle only. That's also interesting, because mod of z is equal to 1, but it will move twice the angle anti-clockwise. Okay, so I am moving my z anti-clockwise slowly, and z bar will move twice the distance anti-clockwise, and z square will move twice that angle anti-clockwise, and z bar will move the same angle in clockwise fashion. This is how these 3 points are going to vary on the unit circle, and we have to figure out the situations when z bar is pi by 2 ahead in phase as compared to z square. So if we move a very small angle, we see z bar is not pi by 2 ahead in phase. You see z square is here. Z square is here, and then z bar is much more than pi by 2 ahead, right? So we have not got a solution still. For this z, this is not going to happen. Let's move the z to this point here. So this is z is equal to I. And then where should be your z square? Let's say first z bar should be minus I, right? So we moved some angle in anti-clockwise way, this thing moved clockwise, and then z square will move twice that angle, and it will come here, right? Minus 1, z iota square is minus 1. So we have this situation, and I think when we do that, this is where we get the first non-trivial solution, z is equal to I, because now you see your z bar is pi by 2 ahead in phase as compared to z square. So this is our first non-trivial solution. Okay, between these two situations we would have no solution, because you see, as we are moving from here to here, this is moving closer and this is moving in this direction, and then when we reach when the z reaches here, then they make an angle pi by 2. Before that, the angle would have been greater than pi by 2. Okay, so this is your first solution when your z is here, z bar is here, and z square is here. Okay, now let's start to move my z. Now if I start to move like in this way, the z square will move double in this direction, and z bar will move the same angle clockwise in this direction. So then you see that the z bar will be coming closer to z square, and you won't get any solution. But there is something very interesting will happen here, that they might coincide, and we could have also solved for this thing z bar is equal to z square with this same geometry. But let's not solve this, we will get confused working at two things at the same time. So let's keep our focus, but just telling you, letting you know that when your z will be at this 120 degrees, when it moves 30 degree, this will move 60 degrees like this, and this will move 30 degrees. So they will come at the same point, because this angle is 90 degree, right? So understanding that, then these two complex numbers z bar and z square will coincide. So notice we have only completed this part of the circle, and we have got only one solution here. We have to still cover a lot of circle, so let's clear up the space. We are solving for this equation, and we have this unit circle, we are here. Now we want to move forward, and let's move in. Now like the second solution is a little bit far away, because when you move z here, your z bar will move in this direction and z square will move in this direction. So the angle between them will be much greater than pi by 2. So we have to cover a lot of distance for this thing that the z bar is pi by 2 ahead in phase to get that solution. So let's move freely to this point. When I am here, my z bar will come to the same place and z square will go there. Now you see that the z bar is pi ahead. So let's be careful, we are going to get a solution now. So pi ahead, 180 degrees. This thing needs to travel 60 degrees and this thing needs to travel, sorry, 120 degrees. This thing z square will travel faster, 120 degrees, and this thing z bar needs to travel 60 degree for the reconciliation to happen. Okay, so we are not thinking about reconciliation. Now the angle between them is 180 degree. We need to reduce 90 degree only, right? So this should move 60 degree and the z bar should move 30 degree. So we will get z bar again. So for z bar to move 30 degree, your z should move 30 degree down, right? So z moves 30 degrees down and z bar moves 30 degrees up, and z square moves 60 degrees, and then we got a perpendicular. Z bar now again pi by 2 ahead in phase than z square. It's a race. It's a fantastic race. Anyway, so we have got the second non-trivial solution at this. For this, this angle is going to be pi plus pi by 6. So you can write this is z is equal to e to the power I 7 pi by 6. Okay, how about now the solution is going to get delayed. Now you can move freely, like you move here, then your z bar will be here and z square will be here. So z bar still 270 degrees ahead in phase, a lot of distance to cover, right? So let's move 60 degrees. Z, we move z 60 degrees, so this will also move 60 degrees and this will move 120 degrees. How much is that? 180 degrees we have moved, and now you see that the angle between them is 270 degrees, so it will reduce to 90 degree. Okay, we've got another solution. Great. So you see that this is now perpendicular. So you moved 60 degrees, so this angle is 30 degree. This solution you can write as minus pi by 6. You can also go like from here 270 plus 60 degrees and in whatever way. So you've got the third solution now. And then we are almost finished. Our z is here. Let's come back to the origin, and all of them will come back to the, not origin, sorry, complex number. Z is equal to 1. Let's come back to this 1, 0 point, and all of them will come back here. Wow, so we've got 3 solutions, right? We've got 3 non-trivial solutions and 1 trivial solution. So total 4 solutions. Okay, now let's move on to the algebraic solution that you can also give. Maybe it is shorter, but it doesn't have that that interesting, that beauty involved with it. Or who knows, maybe somebody sees a lot of beauty in algebra. But anyways, so this is when you have to solve this equation, you take mod and then you come to here, like z is equal to mod z is equal to 0 or mod z is equal to 1. So mod z is equal to 0 will give you a trivial solution. We talked about that. Mod z is equal to 1, you can write like this kind of complex numbers, e to the power I theta plus 2k pi. You know, when you have done nth roots of unity, that this 2k pi could matter. This 2k pi could matter. So let's be safe and let's say that our z is somewhere on the unit circle. So its modulus is 1. So its modulus is 1, and its argument is, if it is theta, it could be written in different ways, plus 2k pi. Okay, and you put k is equal to, k belongs to the set of integers. So this is the general expression for it. So we will try to be safe and complete. So z bar would be like this, you know. So if z is like this, your argument will get will be negative of whatever the argument of z is, right? If your z is let's say here with some argument 60 degree, then z bar will have an argument minus 60 degrees. So that way I just multiply a minus here. Okay, and then I, you can also write I in like this. It has a phase angle of pi by 2. Iota is here. So you have pi by 2 phase angle, but you can write this pi by 2 by adding and subtracting the multiples of 2 pi. So n belongs to integer, that's why. and plus 2n pi you can just write. Okay, and then you write z square, you write double of the argument, and then you frame the equation. So z bar is this, I z square is this. First you have this thing is I and this is z square. Pretty complicated, right? So you club it in, law of exponents you are using here, adding the powers, and then for these two complex numbers to be same, they have a modulus of 1 only, right? They have a modulus of 1 only. It's just that their phase angles should match, or maybe they can be at a difference of some multiples of 2 pi. So that's why I again add 2m pi here, m being another integer. Okay, and then we figure out what theta is. So 3 theta is this, so theta would be like this. So you see this is giving you minus 6k pi, and by dividing by 3 you will get minus 2k pi, and this part here. So minus 2k pi is not going to change anything, right? So minus 2k pi is not actually going to change your angle. So if your angle is 30 degree and if you add or subtract any even multiple of 2 pi, you are going to be at the same place. So you will get the same solution. So I will exclude that minus 2k pi and just think in terms of m and n. M plus n is also going to be an integer because m and n are random integers. So m plus n, I will replace it by L, another integer, and I will start putting values for L. So 2 pi by 3 is 120 degrees if you like degrees, and minus 30 degrees, and then I can start putting the values of L, and then I will see how many distinct solutions do I get. If L is equal to minus 2, I start with a minus 2, I get 210 degrees. If L is equal to minus 1, I get 90 degrees. These are the solutions which we already got before. If L is equal to 0, I get minus 30 degree. You remember that minus 30 degree Z. And then for L is equal to 1, I will get minus 150 degree, but this is where I start to get the same phase because 210 degree is minus 150 degrees, right? If you go 210 degrees, you go 180 and then 30 more. So plus 210 degrees, this phase is identical to minus 150 degrees, right? Check it. You can add both of them, 210 plus 150, they will give you 360 degrees. So, okay, so we have got 3 solutions, and then you will see that after minus 150 degree, you can check for other values, the values will start, the phase angles will start repeating themselves. So you will get these 3 distinct non-trivial solutions, which will make a total of 4 solutions. Okay, and of course z is equal to 0 will give you z is equal to 0, so 4 solutions. The answer should be 4. Okay, next we will move on to okay, yeah, so this was not completely algebraic. This was like we were using Euler's formula here, and who does not love Euler? So we are using Euler's formula here. We can go completely algebraic, x and y. I think this is the most simplest solution for this one, but then again the geometry behind it is lost. But you can do it very simply. Z bar is x minus iy, z squared is this. You make an equation in 2 variables and you get this equation. So you solve for these 2 things. If this is equal to 0, both of them should be 0, right? This thing should be 0 and this thing should be 0. So how would you solve this? So this is 0 and this is 0. Okay, and this 0, the first condition will give you this is equal to 0 or this is 0, you know. So remember, and or is very important here when you are solving 2 equations at the same time. Sometimes you have a common sense, you use that, and but sometimes it's better to be formal. So you see, this is like this condition is A, this is union B, and then you have intersection with C. So you can distribute the intersection on union, and you can go like this. So x is equal to 0 and this, or y is equal to minus half and this, and x is equal to 0. If x is equal to 0, you put here, and this is in AND relation. So this and this both needs to happen. So this is already happening. You can put this condition in this equation and you get that. And similarly, you put y is equal to minus half in this other condition, and you get this equation. Okay, so then this will solve out to be x and y is they are real numbers, right? When you write x, z is equal to x plus iy, x and y are belongs to the number of a real number set. Okay, so then you get from here, you solve this, from here it gets this. So what do we get? Then again you have to distribute the intersection on union, and then you get these 4 solutions. You can verify it, these are the same solutions which we got before. Okay, so 2 questions we have done. Now let's move on to the third one. Third one is not that interesting. It's just it requires a little bit of rigor to solve it, and you have to be in the question. It's not that difficult. So you see, in this question is about z bar denotes the complex conjugate. Okay, fine. Z is a non-zero complex number, so this time you can't take 0, z is equal to 0. In the previous question it was allowed, for which both real and imaginary parts of this are integers. So they are basically saying that this expression is a plus ib, where a and b are integers. Okay, so what could be what are the possible values of mod of z? So you see 1 by z, whenever I see 1 by z, I like to write it as z bar by mod of z square. You can understand why. So I will do that here also. Then I will get my z bar squared common. Okay, so this is a complex number. This whole part is a real number, and you take modulus on both the sides. So this part will just come out of the modulus as it is, and this will get modulus. And this will be root a squared plus b square. Fine. So you make a beautiful equation here. Z squared plus 1 by z square is root a squared plus b square, and then you square it because I see this power is 1 by 4 in all the options. So I am willing to go into mod of z to the power 4. So you can go it simply, because when you square on this side, you will not complicate this thing. You will just get a 2, a squared plus b squared plus 2ab, and 2ab will be 2 here, and that things will this square root will also go. So now you have you can put z to the power 4 is equal to x, and this thing as alpha, a squared plus b squared minus 2. This form is important. We'll talk about it later. So now we are here, and alpha is of the form a squared plus b squared minus 2. This is important. Now we are here, we simplify it. X plus 1 by x is equal to alpha. You solve for it, you will get x is equal to this, and x is mod z. So mod z to the power 4, sorry. So this is mod z to the power 4. So mod z is this expression. And then you see what is going to happen here is that you have a 2 in the denominator and power 1 by 4, and above these are all integers, right? Because alpha is of the form a square plus b square minus 2. If a and b are integers, so a square plus b square minus 2 will also be an integer. So this is an integer, and this alpha square, alpha is an integer, square the alpha and subtract minus 4, this will also be an integer, right? And so these are all integers. So how the hell can we get these 4s here and 6 here? So how can we get a 4 or 6? Sorry, 4 and a 6 here. So it can only happen if you multiply a 2 here also, and then you can see that there will be a 2 multiplied to this whole thing, which should come out as a factor, but I don't see a 2 common factor here. Neither do I see a 2 common factor here. Neither do I see a 3 common factor here. So these 2, because of this form, I would say that these 3 are not going to be the answer. The only one which could be the answer is the first one. So for that, you see that alpha is 43 and alpha squared minus 4 is 1845. Do some calculation, and this is 3 times 205. So this seems like this could be the answer, just that the alpha follows this form. If alpha follows this form, and then you see that a squared plus b squared should be 45, and which can happen with 2 integers. This is a perfect square, 36, and 9 is also a perfect square, and the sum of that is 45. So this can happen. So the answer for this one should be only A. Although it was a multiple choice question, I thought about it for a long time, but then I said no, I should go with A only, because I don't see B, C and D coming. Okay, so that's it. Thank you.